I want to thank Professor Reichmanis for coming to talk today. She's faculty in the School of Chemical and Biological
Biomolecular
engineering, and comes to us, or has come to us by way of Bell Labs, and just recently won the, or was awarded the Byers professorship. So kudos.
Thank you.
And,
Thank you.
Without further ado, she'll be talking to us about polymeric semiconductors, charge or molecular ordering, charge transport, and macroscale mobility. So thank you.
Okay, thank you very much. And I'd like to, it's really a pleasure to be here to talk to you about some of the research that I've been involved in and is ongoing in my group. I would ask that if you've got any questions during the course of the talk, feel free to ask as we're going along, and I'll try to answer. All right, so if we look at polymer semiconductors and the role of molecular structure, ordering, and the electrical performance, if we go up one level, polymer semiconductors sort of play a role more broadly in sort of a general area of polymers that are used in electronics and photonics. So if you think about anything that you have, I left mine in my office, but if you've got a cell phone, computer obviously, if you've got a brand new dishwasher in your apartment, or if you've recently bought a new washing machine, chances are it's powered or controlled with some sort of device. And polymers play a role in the fabrication of those devices and in how those devices operate. All right, so they certainly were involved in the ability to take what was the first single crystal silicon device that was fabricated at Bell Labs over 50 years ago now to what are today nanometer scale device structures that are fabricated routinely and are used in advanced computers and advanced applications. More recently, polymers have become of interest for the development of what is called flexible electronics or plastic electronics. There could be an interest in these materials for applications ranging from transistor-based devices to solar cells, possibly integrating these materials into sensors. And there's also an interest in possibly extending the flexible technologies into more biomedical applications. So there are a whole range of different applications that plastic or polymer flexibility permits that is very difficult or impossible to do with harder inorganic-based materials. And then polymers are also playing a role in photonic technologies. And here are some MEMS devices that were fabricated for a telecom application. And these are some nonlinear optical modulators, again, modulators that are used in telecom applications. All right, so polymers are basically everywhere and somehow involved in just about every technology that we are coming in contact with. All right, so if we look at the materials and the processes associated with polymers for electronics and photonics, you can think of them in a couple of different areas. The first one would be sort of lithographic materials and processing. How many of you are familiar with sort of the lithography associated with silicon device manufacturing? Yeah, so if you're using the clean rooms here, chances are you've been involved in the lithographic process, the gunk that you put down on the silicon wafer that defines the features for the circuits, is a polymer material. You expose it, it undergoes a change in solubility, you develop it, you transfer the pattern into the substrate, you get rid of the polymer. A lot of chemistry, a lot of material science involved in the design and development of those materials and processes so that they're controlled and that you get very reproducible results whenever you run the same process. Dielectric materials are also used in traditional silicon device applications. They can be used for packaging applications. They can also be used as the passive layer within the device itself. And there's interest in developing polymers that have both very low dielectric constants and very high dielectric constants. All right, so both of these systems sort of go back to more traditional device structures. All right, but then there are organic semiconductor materials for plastic electronics. And specifically, I'm going to be talking about polymers for plastic electronics, where the polymer material itself is now the active device layer, and it could be used for a flexible circuit, such as the ones that are shown here. And these are plastic circuits that were developed in the Center for Organic Photonics and Electronics here at Georgia Tech. All right, so there's an active interest at Tech in developing sort of active polymer materials technologies for device applications. All right, so if we look at plastic electronics, what are the advantages? Why bother? All right, so silicon-based technology is not particularly inexpensive to set up. This is a few years old, so that $3 billion fab to set up a new facility is probably substantially more than that now. And all the processing absolutely has got to be done in a clean room environment. Features are definitely smaller than 100 nanometers. Today, probably need to be smaller than 20 or 30 nanometers, going down to, I think, there's research in developing lithographic process technologies for a 14 nanometer node. That is an extremely small individual circuit element, requires a lot of control, and it's not going to be inexpensive to be able to do that. The substrates are rigid, inflexible, roughly 12 inches in diameter, getting bigger. So if you think of the pizzas back there, that's the size of the silicon substrates that are used in a traditional device processing environment. And the processing is subtractive, so you end up wasting a lot of material. All right, if the alternative technology could be developed and implemented so that it's robust and reliable, the advantages are that instead of using very expensive lithographic equipment, we now may be able to use very cost-effective printing technology, such as what's used for printing newspapers. All right, so you could use a printing press, inkjet printer. A lot of very inexpensive technologies would be available. You may be able to do very large area, roll-to-roll processing. You could use flexible, bendable, conformable substrates. Could be paper, could be plastic. And we can use additive ink-like processing, where the only material that you're using is actually going down to where you want those device features to be. All right, so you're using less material, there may be less waste, we'll be using less solvent. So overall, there's a possibility that through all printed plastic electronics, we may actually have a somewhat more environmentally friendly technology, though that is open to question. And when you see some of the synthetic approaches that we've been doing in our labs, you can definitely question whether this is really an environmentally friendly approach as opposed to a very complicated organic chemistry synthesis approach. All right, so what's the determining factor for sort of the figure of merit for semiconductor technologies? All right, so the particular parameter that is being looked at is sort of the mobility, or as measured in centimeters squared per volt second, sort of, well, how quickly does an electron or a hole, does a charge, travel through a particular film when you apply an appropriate voltage. All right, so single crystal silicon, which is used for IC devices that are ubiquitous, has a mobility well over 1,000. So in terms of polymer technology, replacing single crystal silicon, forget it. You know, that's not going to happen. Polysilicon, that's used in a number of different applications, is about 1,000. Amorphous silicon is in the range of about 0.1 to 1 for its mobility. Carbon nanotubes are in the range of 100 to 1,000. And then you have organic materials, whether it's single crystal materials down to polymers, that are in the range of about 0.1 today up to about 1. All right, so that range is pretty comparable to what amorphous silicon can do. And the advantages there are that the organic materials may be more flexible so that they may be processed in a way that would use less energy resources. They could potentially be a more environmentally sound approach. And there are applications where you don't need mobilities of 1,000. If you think about backplanes for displays, maybe circuits that are powering RFID tags, a variety of different sensor applications, you may not need extremely high mobilities. You may be able to get away with mobilities that are in the 0.1 to 1, maybe up to 10 range. All right, so you can start thinking about possible applications. And then there are the advantages of the organic polymer materials. You may be able to get more uniform mobilities. I think I'm going to update this slide and delete the less limited by surface states and grain boundaries. I think it's more of a different issue, but there's still certainly issues with organic materials. You may be able to covalently attach receptors for sensor applications. The processing temperatures are most likely going to be much more moderate, maybe low temperature processing. You can do solution deposition and cover a very large area. There's mechanical and thermal compatibility with plastic and other flexible type substrates. And through the molecular architecture, you may actually be able to rationally control the electrical performance of the material for a desired application. Right, so what are the issues, though? You're thinking about charge transport. There are certainly materials, device, and process issues. All right, so from a materials standpoint, we definitely need better materials, whether it's the conductor, whether it's the gate dielectric, or whether it's a semiconductor. We need enhanced performance. From a device perspective, what is actually happening in the organic material? We understand a lot about inorganic semiconductors and how they operate. Some things transfer from the inorganic area to the organic polymer area, but there are also things that are different. The materials do behave differently, and what are those mechanisms, and how do we control things such that we get the performance that we want? And then there's a lot related to the processing. How do you actually identify very critical bulk and surface effects? How do you, through processing, improve the semiconductor properties? And very importantly, you're coating a very thin film. You have a morphology associated with that film. How do you now control that morphology so that you get optimum performance, but as you'll see later on, more importantly, reliable performance? All right, so that gets me into sort of broadly the research that I've been involved in since coming to Georgia Tech and for a few years at Bell Labs prior to deciding to come here. All right, so I'm looking at polymer and hybrid materials and processes broadly for plastic electronics and photovoltaic applications. We're exploring the design and development of new materials chemistries. We want to try to develop structure, property, process relationships that as a whole we can use to design more robust materials and processes. And we want to understand and utilize mechanisms that are available to us to control the evolution of thin film morphology during solvent processing. All right, so it's the relationship between the structure of the material and the processing and the ultimate properties that we're trying to understand and then use to develop better materials and processes. All right, and this just shows a few figures of roll-to-roll processing. This is a backplane from the first all-organic plastic backplane for an electrophoretic display. How many of you know what an electrophoretic display is or where it may be used today? Does anybody have a Kindle? Your Kindle most likely is driven by an electrophoretic display. It's a black and white display with a semiconductor backplane. This was the first time that working with e-ink, we actually demonstrated that you could use organic technology for the devices for the backplane and drive the electrophoretic display. I'm not sure if this generation of Kindles that have I don't know that it's this generation that has the polymer-based backplane technology or if it's the next generation coming out, but that is going into Kindles. And the technology was developed initially by a small company outside of Boston called e-ink. And I think they have further licensed that technology to others who are then doing the manufacturing for Amazon's Kindle. All right, so, and then you can see, this is an AFM image of a typical polymer semiconductor, poly-3-hexylthiophene, and you can see a fibrillar-like structure in this film, and depending on how you process it, this can look different. Depending on how you process it, the performance can be different. All right, so looking at that, all right, if we look at the processing from the solution state with an eye towards building an understanding of how processing and structure relate to each other and interact to define the properties of the material, we certainly need to understand the mechanism of conducting channel formation. We need to be able to control the microstructure, understand how crystallinity plays a role in this material, and then there are conjugation effects within this polymer backbone that's a conjugated material. All right, and you can see here 6 different AFM images, all at the same scale, 400 nanometers. Each one looks different, and each one behaves differently. And just looking at these images, there's no way to predict which one is actually better or worse. So semiconductor polymer properties are very strongly dependent on the final thin film morphology, so it's very highly process dependent, and the microstructure development during thin film evolution is not very well understood. All right, so what is known, or what was known? All right, so certainly the radioregularity of the polymer, where these side chain substituents, or how they orient themselves in the polymer chain, which is dependent on the synthesis methodology. That defines lousy performance versus better performance. Molecular weight has been shown to have an effect. This is a low molecular weight material of the same polymer. A very highly crystalline material in the solid state. In terms of performance, it's lousy. This is a higher molecular weight material, not as crystalline, a much more amorphous or multi-phase system in the thin film, but it has very high mobility. And then you can also do a lot of surface functionalization in order to control how the polymer orients itself on the substrate, and then depending on the orientation of the polymer, that can also define how charges move through that film. So we started looking at poly-3-hexylthiophene to try to understand the role of microstructure and how we may be able to tune that microstructure using processing and then also in situ techniques to look at solvent evaporation, or the evolution of solvent from a thin film, and look at what's happening at the polymer during that process. And what I'll be talking about now are some results that we've published with David Collard and my student Avi Ayar a year or two ago, and then also collaboration with Mohan Srinivasaro in materials science, looking at sort of the in situ studies with Raman of what's happening to the polymer chains as solvent is evaporating. All right, so start with processing. Avi, my student, came to me one day and said, you know, I don't really know what's going on, but you know, I've been ultrasonicating the solutions of poly-3-hexylthiophene in chloroform, and I've been seeing color changes and large improvements in mobility, a measure of charge transport. So my first question was, all right, you're putting this polymer solution into an ultrasonication system. It's turning black. Early on, I was trained as an organic chemist. You get something black in an organic chemistry lab, you throw it out, you don't use it. So it was, all right, so you must be degrading the material. You're definitely not doing something the right way. You know, go back and look at it again. And you know, when you see a little bit more, come and talk again. All right, so Avi went back and repeated the experiments, did a lot of photophysical studies, did some very critical control experiments, because what he noticed was he could take an orange solution of poly-3-hexylthiophene in chloroform, ultrasonicate it, it turns sort of dark purpley black, and then he could take that purpley black solution, heat it very mildly to 50 degrees. it goes back to this nice orange clear solution. So whatever was happening was reversible. And we did all the characterization to show that yes, indeed, that process is reversible. So we're not doing anything chemically to the polymer itself. But what we do see is that, whether it's in the solution state or the solid state, if we look at the films or the solutions spectroscopically, there are changes taking place in that material. All right, so we're starting to see bands in about the 600 nanometer region in the solution state that are reminiscent of some of the vibronic structure that we see in the solid films of that material after they're deposited on the substrate. So we're getting film-like properties in the solution state. That most likely is because we're seeing an increase in the planarization of the polymer backbone, and we're probably seeing an increase in pi-pi stacking of the polymer chains as evidenced by the vibronic structure. All right, if we look at the microstructure and its crystallinity, we start off with sort of an amorphous looking AFM image, and keep in mind that this is strictly a surface image at the air polymer interface. The interface that is actually important for charge transport is the one at the dielectric semiconductor interface, which is buried. And we can't really get to that to identify what that structure is, but we can use AFM to look at the surface and sort of infer what may be happening. All right, so for the pristine material, looks kind of amorphous. As we continue to sonicate the solution and then deposit thin films from 30 seconds up to 10 minutes, we start to see what looks like some sort of crystallite-like features forming. And as you sonicate further, you tend to get more of these. Looking at the X-ray diffraction patterns, we see an enhancement in crystallinity of those films as we sonicate more. All right, so we naively kind of figured that better crystallinity obviously have to have better mobility. Well, that wasn't really the case. Rather than better mobility, as we sonicated, we got better up to a point, and then the change in mobility basically saturated. So we could improve the charge transport characteristics, but then we couldn't go any further. All right, and these are the mobility versus sonication time results, and these are the absorption spectra, so you can see what's happening to those bands. All right, the other thing to point out is that one sample to the next obviously isn't the same. The trend is there, but it's not the same. So very clearly, the process is not controlled. And if we want to develop a process that's going to be used in any kind of manufacturing environment for any kind of a product, this isn't going to cut it. All right, so we saw saturation. As a result of that, we started thinking about whether there may be a percolation type charge transport mechanism at play. And just to summarize a little bit, there was almost a 2 order of magnitude increase in mobility with ultrasonication time, and then again it's saturated. All right, so we looked at this a little bit further, and then during that sonication process, it appeared that what we were seeing was a transition from a material that appeared to be largely disordered into one that had phases that were disordered, coupled with phases that were highly ordered, and then ones that appeared to be quasi-ordered. And then going back to the literature, we found a paper by Stephen Holdcroft at SFU in Simon Fraser University in Canada, where he had postulated that P3HT in solid films has sort of a blended morphology composed of these three particular phases. And there's been a lot of additional research that's been conducted recently concerning P3HT and its morphology in films that seems to more or less coincide with this kind of a relationship where there's a balance largely between sort of quasi-ordered and ordered phases that can be optimized to enhance charge transport characteristics. All right, so we got our feet wet with looking at a little bit of processing, what you could do with processing to change charge transport characteristics. And then I started talking to Mohan, and we were intrigued about what may be happening in these films. So we decided to see what we might be able to do using charge transport measurements, but then also looking at in-situ Raman as solvent is evaporating to see if we might be able to understand on a more fundamental level how these polymer chains are associating, and then does that association lead to changes in performance, and more importantly, can we control how those chains associate? All right, so we noticed as we deposit a droplet of P3HT on the surface, drain current fluctuates during film formation, there are percolation effects over time, and microstructure evolves. If we change solvents and extend the time, you see differences with solvent, but they're largely associated with changes in the boiling point or vapor pressure of that solvent. And evaporation rate, it certainly does affect things, but it's not clear exactly how. All right, so we started looking at what happens during this interval where we see the largest increase in drain current in an evolving film of P3HT using Raman spectroscopy. And what Mohan and Min-Sung Park, Mohan's student, found is that by doing polarized Raman measurements, they saw characteristic features of a liquid crystalline phase at a given point during the solvent evaporation process. All right, so what we were interested in determining is whether that liquid crystalline phase is coincident with the increase in current that we're seeing, and if that's the case, can we now induce long-range order in these films using a liquid crystalline phase, and what are the consequences of being able to do that for macroscopic charge transport? All right, so LCD displays are liquid crystalline displays where the dipole of those liquid crystals are lined up, and that allows you to be able to use the LC properties for the technology application. So can we now use liquid crystallinity in a similar way? All right, so looking at this a little bit further, in another droplet, again, we confined it to this one narrow area, and we're also measuring drain current and the Raman spectra simultaneously. All right, and as we're looking at the drain current, we see an initial rise, then a steeper rise, and then a slower rise. So if we focus on this area, it's only about 2 minutes that we go from what looks like sort of an amorphous blob in the spectrum to having very sharp absorption bands that are associated with crystalline poly-3-hexylthiophene. All right, so in this short time frame of about 1,000 minutes of solvent evaporation, we're seeing substantial changes in the material itself. And that's at a point where we still have solvent present, a little bit of solvent present in the film. All right, and just to highlight, this is a Raman spectrum of a solid film of regioregular poly-3-hexylthiophene, which is crystalline, and this is radiorandom poly-3-hexylthiophene that you really don't see much in the absorption spectrum. All right, and these spectra look very much like the bands that we see highlighted in red here. These are solvent peaks, and it's hard to say, but it appears that there's no solvent left at this point, but there most likely is some left in that film. All right, and we can look at the microstructure as the solvent's evaporating and deconvolute it. And basically, we start with a film that has both ordered and less ordered regions in it, and ultimately, at point C, have a largely ordered state spectrum. But then also from this point, as the film continues to evolve, there are additional changes taking place that we're trying to understand now. All right. So how does solvent affect the evolving film and the properties? Are there any impacts where of choice of solvent? We've seen that very definitely solvent can play a role. What about using a binary solvent? All right, so we started off looking at a binary solvent that has high volatility and that may be able to hydrogen bond with the majority solvent. And what we saw is that specifically for adding a little bit of acetone to chloroform as a solvent mixture, as we add acetone, we start to see the fine structure vibronic bands in the solid state spectrum. We see an increase in crystallinity of the films that are deposited from that sample. And depending on the choice of solvent, we can see an improvement in mobility or either no effect or a deterioration in the performance. So we started exploring what may be going on here. And one of the things that we used were the Hansen solubility parameters of the solvent system and its relationship to the polymer. And then by doing an analysis of the solubility of P3HT in a number of different solvents, we could define sort of a parameter space where we have good solvents versus poor solvents for poly-3-hexylthiophene and start to explore what the impact of solubility is now on device performance. So if we look at the solubility of co-solvents for P3HT, certainly the chloroform acetone mixture starts off as a good solvent, ultimately ends up as a poor solvent, so that since it is a binary mixture and the solvents can hydrogen bond, as the more volatile solvent is evaporating, there's an increased concentration of the less volatile solvent, or of the, there's an increased concentration of the poor solvent in the good solvent, and ultimately we end up with a poor solvent. That changes how the polymer behaves in that solution, and then that impacts the device performance. Right, so mechanistically, we think that there is ordering of the P3HT chains that's induced by the poor solvent. And certainly, the ordering of the polymer chains can be influenced through solvent characteristics, and that we may be able to use Hansen solubility parameters as a way of being able to gain more insight into the relationships between thin film morphology, molecular ordering, and what we're ultimately interested in, device performance, so that we can now couple these together for an application. All right, so this has been thus far talking about more process-oriented research that I've been doing in my group. I also have a small effort related to designing new materials and seeing what we can do in materials design, which is very synthetically intensive, but also involves characterization and device fabrication and processing. Right, so the particular project that I'm going to highlight here is incorporating electron-deficient benzothiadiazole into an electron-rich thiophene polymer that leads to improved ambient stability. There's more intramolecular coupling that can narrow the band gap, and we may be able to facilitate intermolecular interactions because of this fused heteroaromatic unit. I'm not going to dwell on this, but this is the synthetic approach that Boy-Fu used to ultimately prepare the polymers. If we look at characterization, certainly there's a bathychromic shift if we go from the solution to the solid state. The material has a low optical band gap. We see dual absorption bands, one of which is an intramolecular charge transfer band between the donor and acceptor, and the other one is an oligothiophene transition for the pi-pi star transition. All right, so we see that there are some molecular weight effects where the higher molecular weight polymer does perform better. While it's less soluble, the polymer chains do tend to aggregate, but ultimately the device performance itself ends up being improved. Thermally, we see a melting peak for one of the materials. This is the higher molecular weight material. For the lower molecular weight material, we actually see two transitions in the thermal analysis. And it's possible that we have a mesophase here, which, again, with the Srinivasaru group, we were able to do some polarized optical microscopy showing that there is birefringence, which may be reminiscent of lithocrystallinity. The films themselves are fairly highly crystalline. There's a despacing of almost 27 angstroms, which is sort of indicates that the side chain packing is sort of in an end-to-end mode, and the pi-pi stacking distance is a little over 3.6 angstroms. And And that's for a 4-thiophene unit, and then the despacing goes down for the 6-thiophene material with pi-pi stacking at about the same level. So what we believe, we're able to get good charge transport characteristics within this material. The hole mobilities are up to about 0.75 centimeters squared per volt second. The higher molecular weight material has a mobility about an order of magnitude higher than the lower molecular weight material. The copolymer hole mobilities correlate with molecular ordering. And basically, we are able to tune mobility by working with the molecular structure of the material. But going forward, I think we also need to look more closely at the processing of these materials and how we can control thin film morphology. So in conclusion, very definitely molecular structure coupled with materials processing is going to influence the electronic properties and the device performance of polymer and semiconductor materials. We need to be able to control not only the structure, but also the processing in the environment in order to have reproducible properties in the devices. All molecular parameters of the structure are going to be important in defining performance, and that is going to significantly impact the process performance as well. And what I need to do is thank my students and the funding agencies, my collaborators and early collaborators at Bell Labs, and ask if you have any questions. Thank you. Yeah.
You emphasize the mobility a lot. So how is the carrier concentration in your devices, and can you tune carrier concentration?
All right, so I believe we should be able to tune carrier concentration by choosing the device architecture and the other materials in the device. That's not something that we have been focusing on. That the work that we've been doing at this point has been how do we now enhance or improve sort of the charge transport characteristics in a simple transistor device. And then once we have that, then our plan is to look at other parameters that are going to be important for other kinds of devices.
So do you have a rough number for the?
I don't off the top of my head, no. Sorry. Yeah.
So what's the mechanism or the hypothesized mechanism during the sonication process that leads to enhanced ordering in the films?
That's a really good question. And one that we'd really like to know what is going on. So looking at the literature, there is some evidence, say for polypeptides, that they can be ultrasonicated, and what that does is it sort of leads to breaking of some bonds within a polypeptide, not of the bonds within a chain, but let's say hydrogen bonding between chains, so that you're isolating individual chains, those chains get extended, and then they come together different ways. What we think may be happening is that with ultrasonication, we may be putting enough energy into the system where the polymer, it's a conjugated polymer, and sort of an idealized structure is that it's a nice linear chain. Well, that's not the case. it's going to be sort of a random, almost coil-like structure. So conceivably, the sonication process is putting in enough energy to sort of open up that structure, and then either parts of the same chain or two different chains may be able to associate, leading to aggregates being formed. But the honest answer is we don't know. Yeah.
Elsa's probably answer if this is what you just said, I don't know, but is it dependent on the ultrasonic frequency? Do you see any changes there, or is there another way to input the energy into the system, like heating, lasers, or something like that? Or is it something?
All right, so heating is not going to do it, because if we take the aggregated system that's been ultrasonicated, we heat it, we go back to the original. So that's not going to do it. So there's some very recent work that we're in the process of writing up now, where very low intensity UV irradiation seems to do the same thing. And that's something we're trying to understand a little bit more. I don't think a low power laser, maybe. High power laser, forget it. It's going to burn it up. I don't know whether it's partly the cavitation process, whether it's a pressure-induced change, whether it's simply the energy that's going into the system is doing something to the polymer chain. But, yeah, yeah.
What did you use as a contact? Drain contact and source contact?
Yeah, so the source drain contacts were gold on chromium.
By liftoff?
I believe by liftoff. And then there were UV ozone clean, washed, and everything. Other questions? Yeah.
You tried sonicating in a different solvent? Say
Yeah.
aromatic solvent?
Right. So chloroform is interesting because chloroform it's viewed as being a quote-unquote good solvent, but it's not too far off the borderline of being a not-so-good solvent. Using toluene, it also works. Xylene also works, but xylene is a not-so-good solvent, so P3HT tends to aggregate in xylene anyway. If we go to something that is a good solvent, like chlorobenzene, it doesn't work. So it's very solvent-specific. We've been doing some experiments of adding a poor solvent to chlorobenzene, and then we start seeing ultrasonication having an impact again. So it is very sensitive to the solubility of the polymer in the particular solvent. Yeah.
What kind of thermal treatment do you do to your films? Because, as you say, after you sonicate it and heat it, it goes back to the
In solution.
In solution.
Right.
What about in films?
In films, all right, so in films, with sonicated material, doing any kind of annealing process doesn't have any impact. What it might do, mild heating, drive out any residual solvent. P3HT, there are literature reports that if you anneal it at 150 or 200 degrees, you get melting and reordering, and mobility enhances. The few experiments that we did trying to do that as a control and a comparison, we burned up the P3HT. So, and it could be that we were not, at that time, we were not in a clean enough environment, and we may have been getting oxidation effects. There are other semiconducting polymers that we've been working on where thermally annealing does lead to orientation and changes in the morphology of the film, sometimes for the better, sometimes for the worse.
Yeah, I mean, given that if you're particularly working with co-solvents, this is going to have a much more influence, because if you're using two different solvents having different boiling points, you are going to require, I mean, the rate of evaporation of those two solvents is going to be dependent very much on your annealing process.
Yeah, so the results that we've done here were all spin coated, and the solvents for the co-solvent system were low boiling, so that the amount of solvent remaining is probably very, it's low. We did annealing those films, let's say up to about 50, 60, 70 degrees, there was no difference.
Sure. Thank you.
Okay, well, let's think.
What's your range of mobility? What's the target for mobility range?
At this point, so mobilities in the range of about 1 are probably quite good to be able to use the material in some simple devices that could be of interest. So I don't really think there's a need to continue to increase the mobility higher. I think what we need to do is improve the processes so that we have reproducible processes. And the other thing that we need to do is figure out how to design the materials so that they will be more stable in an ambient environment, so that if you make the device today and it operates a certain way, 6 months from now, sitting out in the open on someone's desk, it's still going to operate the same way. So I think those are the kinds of challenges that today are more important than simply designing new materials that are going to have higher mobility.
Well, let's thank Professor Reichmanis.